Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were discussing designing of smooth nozzles such that it doesn't produce any shocks in the flow, and I'll just continue from that point. We were talking about from the throat. I'll have an axis symmetry line. From the throat we'll go along a circle up to some theta which is equal to nu exit by 2, and after that point we will create new points on the wall such that these points, if you notice what is happening in this region, it is expanding, the flow is expanding. Now if I keep going this way, I will get velocity vectors like this. As it goes up, velocity vectors are out, right, but we wanted parallel flow at the exit. So now we have to turn those streamlines back. That is the other reason why the remaining lines will be turning back. The remaining wall points are designed such that they will be turning back. What is really happening is this region which is actually sending out expansion fans, these regions that are sending out expansion fans, this is a smooth corner, think about it, it is sending out expansion fans downward. Those expansions, when they come back, they will still be expanding. They will still be expanding. As they are going out, they will be expanding more, but after they reach this and come back down, after this point they are all going to be parallel lines. That is the idea of this other part of the compression, smooth compression wall. Initially we have a smooth expansion wall and then a smooth compression wall. This is the whole sequence of how we will have a nozzle downstream section designed, okay, the diverging portion of a CD nozzle designed. Upstream portion, of course, we won't worry about too much. When we are designing a nozzle, they will just put typically maximum angle of convergence as 45 degrees, and then it will have a small radius here. We talked about this R upstream, and this one we called as R downstream. We can pick R downstream to be anything. R upstream decides the initial line here, very first line with a whole bunch of points on that is given by this R upstream. Okay, we will talk a little more about this after we see some pictures. Okay. What I want you to think about is from the initial point, because of this curve, it is going to be expanding. The characteristics are going to diverge as they go out, and after it hits that wall and comes back, they will all become roughly parallel. Ideally they will be parallel only after the last characteristic, which is your characteristic coming from this corner point, that point of inflection. Okay, that is the point where this theta equal to nu exit by 2 exactly. There will be times if you do not have enough resolution in points in here, you may end up with not going and meeting that point at all, in which case you will not have optimum expansion here at the exit. You will be slightly less or slightly more, or you will have theta slightly varying, it will not be all parallel. Those kind of problems will come up. So depending on your particular situation, you may have to choose the number of points such that there is one point going and hitting there. Okay. Then it will be easier for you to design your nozzle. If not, of course, you can have an algorithm where it will sense that there is the previous point is very close to that point and the next point will be far away. Then you introduce another point here purposely, from there you calculate stuff. It is not easy, can be done, you have to use some interpolation in the middle. I will not talk about that here, it is not so important for us. Okay. I did not use it for my design of nozzle. Okay. Now once you have this understanding, let us go to the screen. I have designed a nozzle for Mach 3 here for gamma equal to 1.4. You can see that this is a throat section, this is your A star location ideally, and I have created number of points on this to be 10, initial points on my initial line to be 10. How did I get these points? What I actually did was, we talked about the transonic solution near the throat. I took a point and I said that that is m equal to 1. Actually it's not 1, it's exactly, I went slightly past that, 1.05 or so. Actually no, yeah, 1.05 is what I used, I think. From that point it's 1.05, and here actually it will be slightly subsonic. We will not pick this point. Okay. So from here I go along the characteristic, some delta y downward, and then I will find the next point there, some delta y downward. I said I just divided this throat height by 10 points, so I will get 9 delta y's here. From there to here I moved that height down along the characteristic, found the exact location from the transonic solution there. I will get my theta and m values there. From there I will go along the new characteristic found by this point to here, again delta y down, find the new characteristic. Like that I am going along one characteristic line. I am going along the right running characteristic fully all the way up to here. That is what I have done here. This is the easiest thing to do if you think about. I have done this first characteristic. Once I have done this, remaining characteristics are whatever we did before. From the second point here, go to the wall, the circle goes and ends somewhere here for me. Till here it is the circle, actually circle ends here for me. Okay. So first point goes there inside the expanding circle. From there I send out a characteristic that will again have 10 points. The third point from here goes there, forms the second point of this characteristic, and then becomes that last point on my expanding circle till there. From there I will get another characteristic, and now you can see that the gap between the characteristic lines are expanding very highly here, and after it reflects on the symmetry line, you can now think about this line going back out this way as positive characteristic, and this line going out this way as another positive characteristic, and you can see that they are still expanding. These lines and these lines are still expanding out, you can see. Okay. Now after that you can again see this one is expanding a lot here, and then when it goes out there it is still expanding. This line is going out there, while the next line, the last line, is expanding all the way out up to here. Okay. That is also expanding, but when they go and hit the compression wall here, and when they come back, they are coming back almost parallel by the time it comes and reaches this point. Okay. This expansion going out from this way is countered by this compression this way for each of the characteristics, and they finally become parallel roughly when they come here. When the characteristics are parallel, you are going to have uniform flow field. Okay. When the characteristics are expanding, then you are going to have increasing Mach number. When the characteristics are converging, you will have decreasing Mach number. Okay. And so here you are going to end up with, after this point I did not plot because that is the end of my nozzle. After that if I plot, they will just be parallel lines going all the way straight to the axis, and from there each of these points will just go back out parallel, and all the Mach angles after this last line will be the same as my exit Mach number Mach angle, which happens to be for Mach 3 it will be some angle whatever it is, sin inverse 1 by 3, it will just come out to be those values in here. That is what you will get here. By the way, these regions Mach angle will not be sin inverse 1 by 3, only after this last line from there, from the expanding circle, after that only it will be Mach 3. This is the last line where it is not Mach 3. Downstream of that everywhere it is Mach 3 theta equal to 0. This is what we were discussing before. So it just comes out to be that. So if I now make a nozzle with this particular red line profile, I will get uniform flow with exit Mach number 3. Of course I checked with the same surface given back to a method of characteristics code, and I got the value or the exit to be 3.05 Mach number for this particular case. So it is not exact, which means I have to have more number of points on this expanding wall to be exact. I did not do that in this case, so we are not exactly accurate, it is just 3.05, small error. I am ready to live with that. Okay. And I would say one more thing, typically if you are designing something by purely inviscid analysis, this method of characteristics is purely inviscid analysis. So if you are designing something for 3.05, most likely you are going to get 2.9 or 2.95 Mach number when you are making the nozzle and running it in experiments, because there will be some effect of viscosity, boundary layer forming, area will be slightly lesser, and because of that your A by A star will be lesser, and you will get lesser Mach number, but you will get almost uniform parallel flow field there, okay, with this kind of design. There is some error in it, so I will say slightly over design in Mach number, so that you will end up with a uniform required Mach number. I have designed one nozzle for 2.2 and we got 2.05 finally, okay. And we also designed one nozzle for I believe 4.1 and we are getting 3.9. So that is the kind of numbers you can expect. It will not be exact, it will be close, it will be slightly lesser typically. Okay. That is one aspect of it. Now I am going to think about another case. Instead of solving for what is the wall that is required to get uniform flow field, now I am going to say I am prescribing a wall. I am prescribing a wall that is straight line nozzle, straight line, straight line. This is my nozzle I am giving. If this is the case I have, of course I have to give a point expansion here. That is the only option I have. It is a sharp corner. I do not have any theoretical analysis for R. In this case you have a radius upstream here, that radius upstream we will use in our transonic flow analytical expression, and I will get our initial line here. But now if Ru equal to 0, I do not have any way of calculating that analytically, because it is a sharp corner. Sharp corners typically analytically it will go to infinity, things do not work very well, curvature is infinite, things will go wrong, okay. Not curvature, radius is 0, okay. So things will start going wrong, and because of that we will not use that method, and I will have to think about using point expansion. Point expansion we already talked about, right. I am going to assume the very first line to be a straight vertical characteristic, and I am going to assume flow here is exactly parallel to my symmetry line, and my Mach number is 1. It is not a very good assumption, but it is the only thing I can do right now. So I will assume it that way, okay. And from there I know the final angle of the wall locally. It can be changing far away, but locally that is the angle, and I should be knowing that. And once I know that, now I can think about from Mach 1 to change to that angle, how much should I turn. So you just give that much of expansion fans here, and how many ever points you want on this you can give. Okay. Typically I will give 10 points, but I have done an example here with 20 points. Anyways, I can choose whatever point I want in here, okay. Now one more detail I want to talk about in this nozzle design. If I had a situation where I do not have that upstream or the radius upstream here, so I cannot use my transonic solution, then I will assume my initial curvature of my initial angle of my wall to be exactly equal to theta equal to nu exit by 2 as from the other calculations. I will directly do this. So what that means is, this R downstream, that radius is also now shrunk to 0, okay, which means all these expansion fans are now coming from this one corner. Instead of it being a smooth wall, smooth expanding wall, it will be a point expansion. That is the only change. Point expansion we already had a routine for it. So you just have to go and put so many points exactly at the same location with that kind of expansion. Now if you look at your nozzle, it will just be a compression wall. This is all you will have, it will just be a compression wall. It is already expanded with point expansion and then a compressing wall, smooth compression wall. This is all it will be. This is what is given in all these standard textbooks as minimum length nozzle. This will be the minimum length nozzle that you can design with method of characteristics, okay. That is assuming I still want uniform Mach number and uniform theta being equal to 0 everywhere. If that is the condition, if I have R downstream, R upstream equal to 0, then I will get only compression, no expansion part. That is the minimum length you can ever get in the nozzle. This is your minimum length nozzle. Typically I will never use a minimum length nozzle as per this design, because if I have a nozzle like this and I make a nozzle like this and go and put it in my flow, if I go and put it in my flow, the flow is going to come here, it will never want to suddenly turn, because viscosity never likes any sharp turns. So it will eventually end up with a big separation bubble. Because of this, your nozzle is not having the real throat here, but it is having some other throat which is a moving throat. It is not a constant throat, because it is going to be oscillating recirculation zone. It will be changing shape once in a while. So your A by A star is not fixed ever. So you will not going to get correct Mach number at the exit, and it is not a steady flow. You will never make a nozzle like this ever if you want to use this in a supersonic tunnel. Should never make this. I would say it is better to use a straight line nozzle with a small curvature than this nozzle. Okay. This is the worst nozzle you can ever make, but a better one to make will be with this radius here and then another radius. Now it will just be expanding smoothly, slowly, that the flow is seeing only small turns at any time. It is going to turn slowly, and it will follow the wall very nicely and finally come to exit value there. Okay. This is what you will get finally. So this is a good thing. If I think about it this way, it is a better way of designing a nozzle. There are other conditions you can impose on nozzles, which I will just give it as an exercise or whatever. I do not even want to give it as an exercise. If you want, you can go read up more on raw nozzles. Okay. Raw nozzles have different conditions. That is not same as this m is constant and theta equal to 0. That is not the same condition. They obey some other rules. You can come up with different rules for different cases. Okay. But you can think about that also if you want, but I will not go into that in this course. So as of now, we will go and study a case where I have straight line nozzle like this. Of course, you should know that if I make a nozzle like this in real life, it is going to have a small bump here and a recirculation there. So it will not give me correct Mach number and steady Mach number. It will never give that. So I will just assume that those things do not exist. Viscosity never exists in real life, I will assume, which is really absurd. Anyway, I will assume that, and I will go about doing calculations with point expansion here. And how many ever points I put here, say I put 5 points there, I will have 5 characteristics coming from there first, and the first characteristic is a useless one, it is just a straight line thing. Only remaining 4 will be useful, and I will finally see that I have 1, 2, 3, 4, 5 points. If I started with 5 characteristics with the first characteristic going vertically down, that is m equal to 1, I will end up with 5 characteristics, 5 points on my final characteristic. After that, if I keep advancing along right running characteristic, I will always be having 5 points. I will always be having 5 points in here. Okay, depending on how many points I start with, that is the number of points you will always have after you have reached the steady condition. I can keep on drawing this mesh like this. Okay, we will go and look at on the screen some example of that. This is that straight line nozzle, that red line is my nozzle wall which I am forcing, and the flow is going starting from this point. There is a vertical characteristic which I have not drawn, and there are other characteristics, 20 of them. The first one goes straight vertical, second one goes to this point, third one goes through this point and this point. Like that, there are so many of them. The last one goes through this set of points here on the end till here. That will be your last characteristic. So after that whole thing, you will now find that I have started with 20 points. So you will find that from here you will be having 20 points along this overall. Okay. Now the next thing I need to do is just, this point is now useless, that's its job is already done. The next point here, now I can send it to the wall. I do a wall point calculation here. From there, that point and this point together, I will do an interior point, I get this point and the next characteristic line point, I get an interior point like this, and I just keep on going along this line. That is this picture. Now I also want you to look at one more detail. The very first characteristic was vertical, and the second characteristic was here. that is having the biggest gap between these two, right, and that gap is propagating. If you noticed that gap, the first line just comes and goes back up vertical, this line comes here and goes like this. So the gap between those two characteristics was this big, and that thing is continuing to propagate down here. Okay. It will be more obvious in the next picture. I just zoom out a little more. It's the same set of points which we were looking till now. We were zooming in only this region. Now I am seeing a little bigger picture. And I see here that gap, if you notice, is actually slightly decreasing. Why? This wall is not a nice wall. It's not a well designed wall. Okay, this wall is such that it is going to give you compression after the initial expansion. So it's slightly decreasing, but not very much. They are almost going parallel in here if you think about it. And this gap will always exist. It is going to propagate through all through your flow field. It's going to keep on propagating. Okay. So as of now, I have been solving left running characteristics all the way till here. Okay. And suddenly, if you want to switch to a right running characteristic way of solution, I can still do it, and that is what I wanted to show here. That I have given a different color. Okay. I will start solving from here. I will give a triangular patch here. Okay, this triangular patch where I will from here go to the axis. From the axis, I will now start calculating interior points up to here, and then the next wall point will be here. That I won't worry about right now. And similarly, I will just take every characteristic to the axis. From there, I will just go this way, all left running characteristics. If I want to switch from right running to left running, I will be having to do some patch like this. If I already had a right running characteristic pattern, I did not draw the full fabric. I just drew one set of threads of the fabric. Other set of threads will be this way, which I did not draw. I just put points there. If I had drawn that, then you will find that this set of characteristics are right running characteristic. If I wanted to continue with right running characteristic, they will all be just running like this, parallel, 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 like this, all the way up to there. That's what it will be. And if I wanted to turn it to left running characteristic, say I had right running characteristic all the way here, and I wanted to turn it to all left running characteristic, I had to create this triangular patch here. At the end of it, I will have all lines this way. After that, I can continue along this way. In any case, if I want to go from one family of characteristic to the other family of characteristic, I need to have this triangular patch. This is how I can show it to you much more clearly here. Till now, I was solving left running characteristic from here, and suddenly I switched to right running characteristic. The reason will be more obvious in the next picture. I wanted to study the flow around the center of the nozzle, not along what is happening in the boundary. That is not what I was interested in. I was interested in what is happening in the center line. So I wanted to go for right running characteristics. Yeah, I talked about this already. So this is that triangular patch, and you can see that that initial expansion gap is still propagating through all the way up to here, and in fact you can see that it is going through this region also, between this point and this point, between this point and this point, it is just going through this way. Okay. But the gap will always be there. Okay. That is the only way it will be. Now if you look at it, I have gone to this point and the nozzle wall ends somewhere there. These kind of problems will always come up in solving these kind of problems. You find that the nozzle wall exists up to here, but I can calculate only this point, data point. If I want to be much closer, I should have started with different set of number of points here. Then I can probably get much closer result. Okay. The next characteristic that goes from here, let us say this line, if it goes up, it will go through this and go and have a point out there which is outside of this nozzle. That is the next best I can do. So what I will do is I will live with that point or live with this point as the exit. I chose the next point as the exit. Okay. I chose this point as exit even though my nozzle has stopped somewhere here. That is just cheap calculations. If you want more accurate, you have to do much more number of points here and get it as close as possible to this value and then live with that value. I just did not bother. And after that, I gave a exit pressure boundary condition where the Mach number should have been 8, while this exit for this nozzle was supposed to be 4. And by the way, since it is a straight line nozzle, at the exit, at the topmost point, the theta is not going to be 0, but it will be whatever is the wall angle, right, it is enforced by the wall. So it so happens that it is starting from 15-degree angle there, and if I go down straight it will become 0-degree angle at the symmetry line. That is how the flow will be. In fact, you can still see that expanding region, it is just bouncing up and down across, and that is your initial expansion fan from the throat. This is what will be the problem of not designing a nozzle very well. If you do not design a nozzle very well, you will start having either an expansion fan coming into your flow field or a shock coming into your flow field. It will just be bouncing up and down, up and down, up and down, and finally it will reach your flow field region, which is of interest for us. Okay. If you design a nozzle really well, then all the characteristics are going to be exactly parallel, and there will be nothing expansion fan or compression fan that is coming into your region. Okay. That is the reason why we want to go for method of characteristics to design nozzles. Okay. Up to here, we did not consider any cases where there will be shocks produced. I could have had I did not solve for, after this the next characteristic point I have to solve for will be from here, send out pressure boundary point, from there it will just continue pressure boundary this way, and you will realize that the plume of this nozzle jet is coming out to be this big, it is going to be something really big along this line, it will be this big. Okay. The flow is going to go all the way around up to there. That is what you should be seeing. I did not show you that case, probably I will try and show one picture of that next class. Now what if I chose a pressure outside, the back pressure, to be such that it is a over expanded nozzle condition? Then what will happen? There will be a shock at the exit. If that ever happens, then you will be in trouble. Typically what happens is you will have characteristics crossing each other. That is the thing I want to talk about right now. We already talked about it a little bit in terms of expansion. We said if there is a wall like this, my characteristics will be going away from each other, but if I had a wall like this, I said my characteristics will come together towards each other. Now if I do not bother about their crossing each other and I just keep calculating using my interior point codes, what I will have is a funny situation where I will just draw that case here. Say I had a case like this. If I keep solving this, you will get to a situation where the first line is crossing the second line, and then the second line is crossing the third line will cross the fourth line, like that. So if you think about it, when I start solving, I will solve in a logical order, right. We will just say I will go meet with the first point and then use that and this point to get the second, and then from this and this I will get this, from this and this I will get this, like that. That is the way we will go. But when things are switching around like this, you will start having problems. Till this line there is no trouble. The next line, what will we do if I do not worry about anything? I will calculate this point first. For line 1, I will label these lines. Okay. For this particular characteristic, I will solve with line 1 first, and then interior point with line 2 will give me a point somewhere here. It will give me a point on the back side of the point, and then from there everything else is nice. So, it will just go like this. If I have another point, first line is here, second line is here, third line here, fourth line here, fifth line here. This is the way it is going to be solving. Okay. If I think about one more, I will draw one more and then I will stop. First line it goes here, second line will be here. Actually, I will draw it much worse than what it is. Now my third line is more upstream, so it will go here, 1, 2, 3, and then now comes my fourth line which will be out there, and then a fifth line, and it goes. If you think about what is really happening here, if I imagine this to be a MOC fabric, if I imagine this to be a fabric, there is threads interleaving across each other. Now I can think about a situation where I have this piece of paper, I take this one corner of the, imagine this to be a fabric, I am going to take this and bend it. It is not very nice to bend this. I will actually bring a cloth, there is a cloth there. Okay. So, I have a cloth, okay, and I am going to imagine this, I will keep it here. I will imagine this to be wrinkled like this. Okay. If it is wrinkled like this, but halfway through it is not wrinkled anymore. This side is not wrinkled, suddenly it is wrinkled from here alone. There is some triangular overlapping region. If I have something like this, and if you imagine each of those threads that are going in and coming out like this and going back like this, that is exactly what is happening with your method of characteristics, the characteristic mesh. If you think about it, these lines are just going, these are just cutting through with this. Okay. If such a situation ever happens on your characteristic mesh, then you are having a situation where there must be a shock replacing this whole set of regions. If you think about this, that is what is happening here. This region has gone on top of this region. This has gone on, this region of the cloth has gone on top of the other region. When that ever happens, then I have to think about replacing this whole region here with a single shock. Okay. What is our common logic from our gas dynamics? When compression waves come together, they form a shock, right? But here we did not do anything about that. We just let the compression waves cross each other and go, which is never the case. When compression waves come together, they cannot ever cross. The second wave cannot cross the first wave. They just both club together and become a stronger wave. That is all it can do. So all I have to do is just replace this whole region by one shock, which will take care of the flow field before and after this whole situation. Okay. I will not go into more details of this. You just have to know that when such a thing happens, there is a shock present in your nozzle. I do not want to go into details of how will I put a line here, what should be the angle, what should be the strength at each point of the shock. Of course, you can do all that with method of characteristics if you go into details of it. I will just not go into too much of that detail. I will just say I can put a shock here with varying angles which will decide my shock strength. It is all oblique shocks, each one will decide my shock strength. I will just leave it there as of now. Okay. That is a possibility in doing this. Now once I replace it with a shock, what will really happen? I will have another case here. I am replacing this region with a shock, then my characteristics this side will not change, but my characteristics other side will lose a lot of points, because I am removing a whole bunch of points in my crumpled cloth kind of mesh and putting one line with it. Okay. So whatever points that are coming this side are now supposed to go in a different pattern. Okay. This is the original pattern that it will see, and if you look at it, velocity vector after this oblique shock, you know the velocity vector here is the angle bisector at any point on the characteristic mesh. Hopefully you remember this. Okay. Characteristic lines are your two Mach angles, which means the angle bisector between this will be your velocity vector direction. Okay. Velocity vector direction for each of these cases is something like this. Okay. Angle bisector. Now when there is flow coming like this and there is an oblique shock like this, flow will turn more up. So it will be like this finally. Final velocity vectors are like this. Now think about this being one set of characteristics. What characteristic will it be? Okay. It so happens that these are all left running characteristic when I look from this point. What happens is when they go there, they are still the left running characteristic, they just vanish. because on that side of the shock is where it has to go. There is no point. If I think about one shock line and a point here, the downstream location will have an angle like this and the Mach number is lower. So what happens is characteristics will be like this. This characteristic never runs upstream of the shock. This is just lost. You will just have one set of characteristics going down from downstream of the shock. This is all you get finally. Okay. You will just have to live with this. Of course, from inside you can still have other characteristics going down here, and maybe there is a wall here and it will interact and come back out from there. Maybe if there is a wall here or an axis point or whatever, depending on that, it can bounce off of a boundary and come back inside and create a mesh field there. That is still a possibility. Okay. But that is a separate possibility. I will probably show a picture of this next time. I do not have a picture directly with me right now, okay, for this case. I will show a picture of this and a picture of pressure boundary conditions, probably a picture of this crossing of the mesh, the cloth crossing kind of thing. Show all these three next class most likely. Okay. But if I am given a flow over a body kind of external conditions, then how will I solve the problem? Say I have a situation where I have some diamond shaped wedge airfoil and I have some supersonic flow, parallel flow incoming. Do I need to give you initial conditions for this problem? Initial line, it is already given when I said parallel flow, uniform Mach number. So I can pick a set of points at some condition and say I know the location of the points because I pick the points, and at all those points I am going to tell the Mach number and theta, right. That is what we need for every characteristic point. I need x, y, theta and Mach number. So I will give all those for all these points. I just distribute set of points here. Now all I have to do is start running characteristics from them. I just have to start running characteristics from there in positive and negative directions. But of course I know it is not useful, so I do not want to draw all that remaining portion. Let us say I will solve only the top half of my wedge, in which case it comes to the symmetry line and goes up. Or equivalently I can solve the full flow field, then this point would have come from here and it is running through from here. That is what will be the case, which is what I simulate by saying symmetry line, it bounces off of the symmetry line. Okay. Ideally it is coming from the other side, it is like a mirror line. So if I think about the next one, it is going to go like this, it is equivalent to coming from here and going like this. Okay. That is what is happening. Ideally that I should not be talking to you guys now, it should have been given to you in some other fluid mechanics course. Okay. But I will go to this point, suddenly I have to give a wall condition there. Till now it was symmetry line, suddenly it is a wall condition. If I just go and start solving with the wall point condition there, you will start having characteristics crossing. Characteristics will just bounce back and go upstream. Okay. Instead, since I know that this is a shock definitely exists in this problem, I can do a better solving procedure wherein I will say I will put a shock first. I will put a shock at the beginning point only, and then when this characteristic comes and meets here, I will find out the point here, the upstream of shock, that is at the point what is the value as if the flow upstream of it is what I am calculating. I will calculate that point and then I will look at that local region. What is that local region looking like? It is a shock with incoming theta is known, incoming Mach number is known at that location xy. So once I know that theta and m, and I know this angle, local angle beta, the oblique shock angle. Once I know these three things, I can calculate the downstream of the same shock at the same location. I can calculate the downstream conditions. So it will finally be going with some other theta and some other Mach number m2 and theta 2. Okay. This is what I will get. Once I get this, as long as m2 is supersonic, I can still use method of characteristics. I can still say I will have characteristics running this way and I can start solving the problem. That is what we will be doing, except for there will be cases where the characteristic on this side will run up. If it runs up this way, you cannot solve it. Okay? You will have this problem. When this happens, some characteristics will be lost, only some characteristics will be useful. Only the right running characteristic will be useful, left running characteristics will become useless. Okay? That also can happen in this case. Okay? Depending on whether the Mach number is very high or not, if you are very close to 1, you can manage having characteristics this way. Most likely you will never have it, always shock will come in and block the left running characteristic. Okay? If there is a left running shock, that will cut the left running characteristic typically. Okay? If that is the case and I still want to solve the problem, and let us say this is not going uniform, the wedge is some other shape, then there should be a feedback from here to that if I want to solve it. How will I go through that? Say I am given some shock point I already know, it could be my very first point. I know some point already, I want to find the next shock point. That is, when I say I want to find the shock point, I want to find the location of the shock and the slope of the shock, which is my beta of the shock. Beta is the shock angle. I want to find those two. So my problem now comes down to, I am given one interior point and one shock point, that is on the shock point. Now I have to find this point 3 from here. That is what is expected. So we have to think about how to solve this. If I had an interior point and I am sending a positive characteristic, it will go and meet there, right. So this positive characteristic will have theta minus nu constant, which implies that theta 2 minus nu 2 is equal to theta 3 minus nu 3. Now I know everything at this, but I do not know anything on the other side. Okay. Say I have uniform flow field coming, I am simplifying the problem, I do not want to complicate the problem. If I am having uniform flow field coming, I know the upstream condition at any point on this curve, it is exactly the same, m and theta are known upstream uniform conditions. Okay. So if I know the upstream conditions, now I will go back to this picture, I am given m1 and theta 1, I do not know beta, I do not know theta 2 m2, because beta only when I give beta I can get theta 2 and m2, but I know that I want a relation between theta 2 and nu 2. In here it is 2, in here it is 3, okay, do not get confused there. The downstream of the shock is 2 in this local picture, but in here it is considered 3. Okay. I know that theta minus nu should be a particular value downstream of the shock, that is a given condition. So now I will tell you that there is only one beta for which it will be satisfied, there will only be one beta at which theta minus nu downstream of the shock will match whatever value we are giving, theta 2 minus nu 2 equal to theta 3 minus nu 3. We do not know theta 3 and nu 3, that is the downstream of the point 3, I do not know the values, but I can find out. So I will iterate on this beta angle somewhere between 0 and theta critical, okay, not 0, mu and theta critical. I will solve. Why am I choosing? Remember their oblique shock curve. I want to stay only in the supersonic section. Okay, of course you know that it will be supersonic, even a little bit more that side, but I will stay only between mu and theta critical and I will solve for this problem. I will just keep on trying whatever beta from here to here till I get to some particular theta value which will match this. If I do not get a solution in this, I will say okay, this is going to have a detached shock and things will get messy. After that the flow is subsonic, I cannot use my method of characteristics to solve this problem, it will become that. Let us say we do not choose to solve such problems, we will choose some good problems which are solvable, then I would say that I can definitely find a beta for which I will reach a particular theta and a particular m such that m2 such that I will solve that theta minus nu function to be exactly matching this characteristic line. That is possible to solve. Once I solve, I am sitting here, Now I can send a negative characteristic down here, which will interact with whatever is on the wall here coming back up, and I will get another point which will go up and find the next point. Okay, like that I can keep on solving. I can keep on solving my oblique shock on some airfoil or something. I will draw a better picture than this once more. If I have a case like this, what I will do typically is use the initial angle here and solve my initial oblique shock by simple oblique shock techniques, whatever we did in simple gas dynamics. Initial angle I will give. After that I will tell one point on the wall that this is the flow field there. I will extend whatever is downstream of here, same value here. After that, from there I will send out a positive characteristic that will dictate the flow field from here. Okay, and like that I will get this point. Similarly, I can start now solving this characteristic this way, which will send out a characteristic, and then I will now get the next point there. Like that I can start getting, and eventually I will start having a full shock which will be curving based on the local wall angles here. This local wall angle decides my theta minus nu on this line, this characteristic line, which will decide the theta minus nu at that local point on the shock. Similarly here, theta minus nu will be, theta will be lower value, so theta minus nu will be different from here, and so this will decide the shock point there. Okay, which is also telling you some gas dynamics physics. If you think about it, the point that has a change here will affect only points downstream of that characteristic, which is our original anyway thinking, the zone of influence kind of thinking. If I have a point here which is causing a change, the change here is my wall decreased its angle. If that is happening here, then only downstream of this region, this region will actually feel the effect of this. Okay, that is what is decided by this particular characteristic line. Why? Because that is the characteristic which is taking the information that there is a change had happened here. All the previous points did not know that there was a change here. Okay. But once there is a change here, now every point on the characteristic knows that there was a change here. If I send a positive characteristic this way, negative characteristic this way, that also will tell the information that there was a change here to all the points downstream here. That is the reason this point knows that there is a change here. How? That point came and told this point. Okay, that is the way you continue in all these directions. Okay, this is what we call a shock point routine. Of course, I did not tell you how to find the location yet. Once you know the beta angle, remaining thing is similar to your jet boundary calculations. We know this is the angle of the shock, and I know the final angle of the shock is this, and it has to be a smooth curve from here to here. I will draw a line from 1 to 3, which is average of this beta and this beta, tan of this beta and this beta average. So that will give me one line here, and the other line is coming from average of theta plus mu from here and theta plus mu from here. That will be one line from here. These two intersection will give me that particular point. Okay, that is the geometrical way of looking at where the shock will be present. Okay, with all this you can definitely solve this problem. So I think I have talked almost about everything in 2D method of characteristics. I will just give you a little bit of axisymmetric method of characteristics. That is, I will just give the equation and say it is solvable, but I will not solve it. Okay. If you go and do the same kind of equations and finally come to a point where d theta plus d nu equal to 0 kind of form, then I will write that particular final expression only. For axisymmetric MOC, you are going to have, instead of y I am using r, because now it is radial versus axial, only two variables that matter now, dr by dx. For characteristic lines, characteristic directions, instead of dy by dx before, now it is dr by dx, d radius by dx, okay, is going to be equal to same thing as before, theta plus minus mu. This is not going to change, this is just deciding our Mach cone direction. But along each characteristic, now I have to specifically say previously we did not have axisymmetric terms. Now because of that 1 by r terms coming here, you have extra terms. If I go back to 2D situation, this 1 by r term will go to infinity, sorry, 0, 1 by r goes to 0, and because these terms will just get cancelled, and I will just get our original expression for negative characteristic, that is negative characteristic is theta minus mu condition. I will have the d of theta plus nu is 0, which means theta plus nu is a constant, which is what we had before. Now it is no more a constant, it varies with r. Okay, that is the special thing here, it varies with r, and you have to slowly calculate for each point, from point to point you have to now take this as your equation and solve for your new values of theta and nu. Okay. Now it is a little more complicated problem to solve. I will not solve, I will just tell you that it is possible to solve this. Okay. And if it is a positive characteristic, then previously we used to have theta minus nu as a constant. Now I am having theta minus nu equal to this whole expression. What m will I use here? Some average m between these initial point and the final point. That is typically what I will do here, similar to the previous techniques. Again I will use some r in between these two values, like that. Okay. I can calculate this, but I will just avoid more details than this. By the way, if you go and use some serious books on method of characteristics, like I will give you the best book I have ever found till now. It is authored by Hoffman and Zucrow. I believe the book has 2 volumes, and the second volume deals with fully method of characteristic solutions. First volume deals with ordinary gas dynamics. They are really thick books. Okay. But if you ever get to see a book by these people, it is really good book on lot of gas dynamics problems. I have used this as a reference also for teaching this course. Okay. This gives you a different approach to method of characteristics. It does not use theta and nu as the variables along the characteristic lines. They use pressure, u and v as the actual values, which actually means that they are not solving this way, they are not using the phi based method, the velocity potential based method, they are solving the actual equations, mass momentum energy equations. Okay. That will be a slightly different approach than this. There you will need 3 lines to be solved, left characteristic, right characteristic and streamline. It used 3 conditions to be solving at every point. The interior point, axis point, wall point, all the routines will be slightly different than what we have used. What I have given is a really simple situation where it is easy to solve. Okay. And by the way, this can be extended to 3D also. People have done 3D MOC also. I will avoid all that. I do not want to give 3D MOC, etc. Okay. So as of now, I have finished my discussion on method of characteristics, except for I will show you some 2 pictures. One will be with the characteristic mesh crossing and crossing this crumpling of cloth kind of situation, and then a case with pressure boundary condition solved, and a case with external flow solved. Okay. That we will do next class, and then we will go to some extra portions other than what is needed for the curriculum. That will be some unsteady flow discussions. Okay. Any questions? See you people next class.